a local path, it will happily go get that URL, I mean the file specified by that URL on a remote server and execute it in your web application. Improper validation of array index. That's a more specific form of. Anybody can guess? Buffer overflow. That's right. Improper check for unusual or exceptional conditions. You have something going wrong in a script running with elevated privileges. You don't check for errors. Maybe what went wrong is that your system got attacked and you don't realize it and you happily continue in a compromised environment. Alright, integer overflow or wraparound. Right, that's when you're trying to do an operation on, let's say, a short, and the result of that operation is greater or smaller than what the short can represent. Incorrect calculation of buffer size. That's again a more specific case of buffer overflow. Missing authentication for a critical function. That's when maybe you have a function that only administrators know about, or it's only called in your code. It's only called by other code that you trust, but you don't realize that it's exposed. Other people can call it. It can be part of an API. You want other people to interact with your system. We talked about download of code without integrity check. Permission assignment for a critical resource. That's obvious. Allocation of resources without limits or throttling. That's obviously when you can make requests that are very expensive for the server but cost very little for the attacker. URL redirection to an untrusted site. It's also called an open redirect. That happens when you have a web application and you're trying to count the clicks. Maybe you want to do attribution, you want to know how popular a file is or a resource is. Maybe there is some sort of scheme that redistributes revenue, advertising revenue, for example. So whenever you click on an image or a link, it goes back to the same website, which records the events and then sends you off somewhere else. Now, that function of sending off somewhere else, if it's open, if an attacker can specify that, then an attacker can give you a URL that looks quite fine. Let's say you see that URL on a forum. It starts with google.com blah blah blah. Oh, it's a search to find the things he was talking about. But instead it's a redirect to a malicious site using a Google redirect. They don't do that anymore, but at some point they did. Use of a broken or risky cryptographic algorithm. That's fairly obvious. And then the race condition, which is when you check for something and then you're going to do something else, but in between the validity of the check can change. So the action could be incorrect, become incorrect in the meantime. All right, there's more. There are profiles. So those profiles are different organizations of the CWEs for different kinds of applications. We can even include CWEs that were not in the top 25. For example, there's an educational profile. It includes the uncontrolled format string, CWE 134, because it's historically been important and it's a useful concept. Also, when we teach people about those, it's because we don't want format string vulnerabilities to be coded by our graduates. So there are additional considerations in each of those profiles. So for the educational profile, that's what I focused a lot on this CWE effort. We use a broader time for prevalence, all historical data that's available, whereas the CWE itself focuses on just the most recent data. Again, that's because we don't want graduates to repeat mistakes that have been fixed and recognized in the past. I added an emphasis rating based on the difficulty of understanding and the usefulness of a CWE for understanding other concepts. So also added a little bit of consideration to how prevalent some mistakes can be by new programmers in the classrooms or in projects. Importance in producing good software engineers, the impact of the weakness, etc. So the final ranking is, again, importance times prevalence plus emphasis. Keep it simple and consistent. Other profiles that are available if they interest you. There's on the cusp, that's a list of those weaknesses that almost made it to into the list. So if you already mastered all the first 25, you can look at those additional ones which we think are, matter. There are weaknesses by language. Only considered 4 languages. Weaknesses that are fixed typically in design versus implementation. Yes?
Which 4?
Which 4? I'll have a table in a few slides that will show which 4. Automated versus manual analysis of the code. And then for established secure developers, the rankings were done only using data from large companies, which have internal training programs and so forth. They can also be ranked by importance. If you're contracting out the development of software for your company, then you may be more worried about the importance of weaknesses. That is this angle. By technical impact, that is a ranking by the consequences of those weaknesses. Here's an example. Weaknesses by language. That's only the top part of the table. So we have C, C++, Java, PHP, and Perl. You can see that the ratings can vary. Sometimes we don't have any ratings. So for example, for PHP file inclusion, it's obviously specific to PHP. Although you might contrive a way of making it happen in other programs, it's not something that other languages are predisposed for. So you can see, for example, one that's equally difficult for all the languages. It's to prevent SQL injection. Or equally easy if you know the solution and you're using prepared statements. All right, let's move on. Things that are fixed in design or implementation. A lot of things depend on how you implement them, but there's also a fair number that depend on how you design your system. And of course, you want to fix things that you can fix in the design while you're designing it, because it's more expensive to fix them later. So that gives you an indication of which weaknesses you should look for when you review your design or when you're at the implementation stage. OS command injection, that's often an implementation issue. Can you think of something that needs to be fixed in the design? And the hint is that we talked about it earlier. No, that's not a design issue. Pardon me? Validation of input. It could be a design issue if you think about using libraries and frameworks that automatically do it. Yes. One we talked about earlier was missing encryption of sensitive data. If you haven't planned for it, it's hard to implement it. Another example is using a risky or broken encryption algorithm. All right, another profile, automated versus manual analysis. The idea is to rate for each CWE, what is your chance of success if you use a white box approach versus a black box approach, and depending on whether you're using an automated versus a manual analysis. Right, automated means using a code scanner, and manual means doing things like code reviews. So, for example, reliance on untrusted inputs in a security decision. If you try an automated method, it's going to be fairly difficult because the code scanner will have difficulty figuring out which of the inputs are used for security decisions. So you'll have more limited success. If you're just given a black box, you don't have access to the source code. If you do a manual analysis, that's going to make it more difficult to figure out what's going on. But if you're given all the code in the white box approach, then you can. It's easier to do a code review. All right. Here's a little bit of the table for weaknesses by technical impact. So they were rated for code execution, information leaks, also called exposures, privilege escalation, bypass of authentication mechanisms, and denial of service. So if you look at PHP file inclusion, you really should worry about the execution of additional code. It may be used for a denial of service, but if you have full access to the machine, why would you bother with just a denial of service? Okay. All right, things you can do with that top 25 list. So you can make sure you know what they are, so you recognize them in your code, and maybe in someone else's code when you do a code review. You should know the mitigations too, so you can apply them while you're developing the code. If you want to learn them, then you should have a look at the educational profile and the guidance for educational users. If you're doing auditing or penetration testing, then you may consider that list of weaknesses as a suggestion as to what may impact your application the most. What